The nucleus, part 6. Now we're going to talk about Aston's curve. Aston's curve is a curve of the binding energy per nucleon of a nucleus as a function of the mass number. If we find the binding energy per nucleon of all nuclei in the world, we find them distributed like this. This curve is called Aston's curve, the binding energy per nucleon as a function of the mass number. When the number of nucleons increases from 0 and onward until 20, we notice a certain irregularity in the curve. Increasing, decreasing, increasing, decreasing, irregular manner. When the number of nucleons exceeds 20, we notice that the curve increases until a maximum when the number of nucleons is 56. This is for iron. Then decreases until 7.6 mega electron volts. The maximum value of the binding energy per nucleon is 8.7 mega electron volts per c squared. The binding energy per nucleon won't exceed 8.7. When A is between 20 and 56, the binding energy per nucleon increases. So the nuclei coming after the previous ones are more stable. We notice that the curve decreases after that. Then the nuclei coming after the previous ones are less stable. We can divide this curve into several regions or zones. When A is less than 20, the binding energy per nucleon is less than 8 mega electron volts. If A is between 20 and 56, the binding energy per nucleon is increasing from 8 mega electron volts until 8.7 mega electron volts. When A is between 56 and 190, the binding energy per nucleon decreases from 8.7 mega electron volts to 8 mega electron volts. We notice that the binding energy per nucleon of a nucleus whose mass number is between 20 and 56 is between 8 and 8.7 mega electron volts. When A is greater than 190, the binding energy per nucleon decreases from 8 to 7.66 mega electron volts. When A is between 20 and 190, the binding energy per nucleon is greater than 8 mega electron volts and won't exceed 8.7 mega electron volts. Outside this region, the binding energy per nucleon is less than 8 mega electron volts. Now let's talk about the valley of stability or Seeger's diagram. Seeger's diagram is a graph of n as a function of z, number of neutrons as a function of the number of protons. In this frame, we plot the numbers n and z of all nuclei. We notice that the stable nuclei are found in this zone. These are the stable nuclei. These are the unstable nuclei, the blue and green dots. The stability curve is called the valley of stability. The valley of stability. All these nuclei in this zone are stable. This is the valley of stability containing the stable nuclei. This is the first bisector in this frame. This is Y and this is X. The first bisector has an equation Y equals to X, hence N equals to Z. We notice that when Z is less than 20, the valley of stability is very close to the first bisector, sometimes confounded with it. We also notice that the stable nuclei corresponding to Z less than 20 are on the first bisector or just above it. We notice that all the nuclei are found in this side of the first bisector. If we take a point on this first bisector of abscissa Z and ordinate N equals to Z, a point above this point has the same Z but has a number of neutrons greater than N. For these points, N greater than Z. In this side, N greater than Z. Hence, all the nuclei have more neutrons than protons. But when Z is less than 20, N and Z are equal or very close to each other. Since all the nuclei are found in this part above the first bisector, then these nuclei have more neutrons than protons. For Z less than 20, the number of protons equals to the number of neutrons, or the number of neutrons is slightly greater than the number of protons. We can come out with a conclusion that N is greater than or equals to Z for all nuclei. If we draw the line that is perpendicular to the first bisector, what is the equation of the straight line that is perpendicular to the first bisector? It is Y equals to minus X plus B. Minus X, since the line is perpendicular to the first bisector. The slope of the first bisector is 1. The slope of the perpendicular to it is minus 1. So that's to say, Y plus X equals to B. Y is N plus X is Z equals to B, which is A. B is constant. A is a constant. On the same line, we always have that the sum of the coordinates of a point is the same constant value every time. For example, let's take this point. The sum of its abscissa and ordinate is 40, for example. Hence the sum of the abscissa and the ordinate of this point is 40. The sum of the abscissa and ordinate of this one as well is 40. The sum of the abscissa and ordinate of this one as well is 40. Similarly, if we take another line that is perpendicular to the first bisector, if the sum of the coordinates of this point is 100, for example, the sum of the coordinates of all the points on this line is 100. Always n plus z equals to 100. Here n plus z is always 40. All these points, this point, have a mass number equals to 40. This point has a mass number of 40. This point has a mass number of 40. But the farther away we move from the first bisector, the number n is greater than z. This nucleus contains more neutrons than a stable nucleus. This nucleus contains the same number of nucleons, but the number of neutrons of this nucleus is greater than the number of neutrons in this nucleus. Here, this and this are two nuclei having the same number of nucleons, but the number of neutrons in this is greater than the number of neutrons in this nucleus. That is to say, the number of protons here is greater than the number of protons in this nucleus. Here the number of protons is greater than all these points contain the same mass number or the same number of nucleons. But the farther away you move from the first bisector, the more neutrons are present compared to the protons. This contains more neutrons than this, and this contains more neutrons than this. So compared to a stable nucleus, this nucleus contains more neutrons, and this nucleus contains more protons. This nucleus contains more neutrons than a stable nucleus, having the same number of nucleons. And this nucleus has more protons compared to the stable nucleus of the same number of nucleons. That is to say, this nucleus has an excess in protons compared to a stable nucleus of the same mass number. Therefore, for transforming into a stable nucleus, a nucleus has to get rid of a proton or a neutron. This possesses an excess in neutrons compared to a stable nucleus of the same mass number, and this contains an excess in protons compared to a stable nucleus of the same mass number.